Imagine a tiny particle of water flowing through a pipe. As it moves, this particle possesses energy. Just like a car speeding down a road or a ball held high above the ground, this fluid particle has energy associated with its motion and its position. But for a fluid, there's a third, less obvious form of energy: the energy stored in the pressure pushing it along. The Bernoulli equation essentially states that the total mechanical energy of a fluid particle remains constant along a streamline under specific ideal conditions. First, there's kinetic energy, the energy of motion. A faster fluid particle clearly has more kinetic energy. It's proportional to the square of its speed. Think of it as the oomph it carries because it's moving, defined as v squared over 2 per unit mass. Next, we have potential energy, the energy of elevation. If our fluid particle is higher up, gravity can do more work on it as it falls, giving it more potential energy. This is directly proportional to its height, z, multiplied by the gravitational acceleration, g. Finally, there's flow energy, often called pressure energy. Imagine fluid being pushed into a region by high pressure. This incoming fluid does work on the fluid already there, increasing its energy. So, higher pressure means more stored energy per unit mass, ready to be converted. This energy is represented as pressure, P, divided by density, ρ. The Bernoulli equation states that for an ideal fluid, the sum of these three energies, kinetic, potential, and flow energy, remains constant along a streamline. It's simply a statement of mechanical energy conservation, but for a moving fluid. This means that if one form of energy decreases, another must increase to compensate, keeping the total constant between any 2 points on that streamline. Crucially, the Bernoulli equation isn't universally applicable. It relies on several key assumptions. The flow must be steady, meaning conditions don't change over time. The fluid must be incompressible, so its density remains constant. And most importantly, it must be frictionless, meaning no energy loss due to viscosity. Also, there should be no external energy input or output from devices like pumps or turbines. Finally, it only applies along a single streamline unless the flow is irrotational. Violate these, and the equation breaks down. Let's see Bernoulli in action. In a horizontal pipe that narrows, like a Venturi meter, the fluid must speed up to conserve mass. This increase in kinetic energy has to come from somewhere, since our total mechanical energy is constant and potential energy is unchanged. So, the increase in kinetic energy must be balanced by a decrease in flow energy, which means the pressure drops. This is why a narrowing pipe creates suction, a beautiful demonstration of Bernoulli's principle.